Professor Sui graduated from UCLA in the mid-80s and go back all the way. And his first job is actually at University of Maryland. He came as a postdoc with me at that time. And I was at NASA at that time. So we since then, we have been kind of work together. And after his stay at Maryland, he actually worked at Goddard for almost 8 years. Yeah, 8 or 9 years. And then he went back. He was recruited back to first to National Central University of Taiwan, where he stayed for 9 years. And then he got recruited to National Taiwan University, where he has stayed. He's currently a distinguished professor over there, and he has been, and all his career, he has been working with modeling and observation of tropical convection and intraseasonal variability, SC fluxes, and many areas. So today he's going to tell us something about a recent South China Sea experiment which had to do with the intraseasonal variability in the Wampu region. Okay, see? Okay, you have.
Yeah. Thank you. It's a great pleasure to visit University of Maryland again. Friends like Bill Lau, Kim Yung King, and Professor Lee, and Liang, Professor Liang, and many other people. So today I'm going to introduce the work I did for the past couple of years on this specific subject, boreal winter and summer intraseasonal variability over Indo-Pacific Wampu region since 2016. This is part of the motivated and focused because I have a project that and in the project we perform a few campaigns in the 2 islands in the South China Sea. So we call this field campaign acronym called SCSTIMX. So it stands for South China Sea 2 Island Monsoon Experiment. Actually, back like in 1998, Bill Lau was the PI for a bigger project called the SCSTIMX, right, the South China Sea Monsoon Experiment. So my co-authors, collaborators, Professor Mengming Lu and Zheng Yuheng are all in the same university. One is in the same department, and Professor Zheng is in the Institute of Oceanography. So the SCSTIMX is the fact. I'm sorry for the Chinese. So the kind of motivation and the background for the experiment, because as you know, the South China Sea and the Maritime Continent linking Indian Ocean and the Pacific Ocean. So the climate, climatologically, it's very important. I think you all know, so I don't have to spend too much time. So we proposed this experiment because the IOP of Maritime Continent, the project, try to make a measurement in this region, and we were asked to participate. So we are kind of doing things in north of the Maritime Continent in South China Sea. Okay, so this is why we're doing this kind of experiment. And so for the scientific issue for this particular talk, I think can be shown by this results from C.P. Chen in his 2005 paper. This is showing the rainfall in color and the monsoon in vector. So this is winter minus summer. So this is showing the winter kind of circulation. So the enhanced rainfall, the monsoon rainfall is in the Maritime Continent region, and in the summer is in the north of the equator over India and the South China Sea and East Asia. So that in this region, because of the topography and the landscape contrast, so the terrain plays a very important role, and the asymmetric seasonal distribution, as studied before by Bill Lau and C.P. Chen and some other people. And this is.
Is it not the clicker not working?
I just maybe push the button here. It's okay.
Oh, that's the laser pointer.
Yeah.
Use the arrows.
Okay. Yeah. Thank you. Yep. Yeah, and also, yeah, my specific interest is about this evolution of ISO and associated processes, and also the extratropical tropical interaction. So this is we call integrated project. We have our 8 sub-projects, and I'm leading one of the projects focusing on this kind of scientific issues. Okay, so we carry out several field campaigns. So this kind of hot diagram along the equator for the SST anomaly and the OAR anomaly is showing for the past 2 years since December 2016. As you know that following the El Nino event of 2015, El Nino 2016 and 2017 is in the La Nina condition. Okay, so we carry out the first pilot experiment in the December 2016. Okay, and then we have a summer pilot study in 2017, and then we have the winter, the specific winter IOP in December 17 last year, and then the summer experiment just ongoing past May and June. So I'm going to focus on the boreal winter interseasonal oscillation for the 2 winters, okay, the December 2016 and December 2017. And also we are going to talk about the summer interseasonal oscillation during the past May and June, and also the climate background during this year. So this is what I'm trying to cover for today. So first, I'm going to talk about the boreal winter interseasonal variability. So this shows the December mean OAR anomaly for the 2016 and 2017 as a contrast, and this is the mean SST anomaly and the circulation. So as you can see, the 2 winters are in the La Nina condition. So the South China Sea and the surrounding oceans are in the anomalous convective stage, and with the cold anomaly over the central eastern equatorial Pacific and enhance the easterly flow. So embedding in this kind of interannual background, we carry out 2 cruises with the research vessel OR1 of National Taiwan University. So we sail from Kaohsiung, southern Taiwan, and then to Taiping Island. This is the Dongsha Island, and this is Taiping Island. These are the 2 islands we focus with extensive observation measured at these 2 stations. And then we come back to Taiwan in about 2 weeks. Okay, this is done in December 2016, and this is done in December 2017. So, first we'll show you the kind of overall interseasonal variability in the 2 Decembers. This is the OAR anomaly in the equatorial region during the December 2016 in the equator, and also north of the equator 5 to 15 degree north, and that's the same plot for 2017. So I think these 2 winters, all in, as I said, in the La Nina condition, they are in very similar kind of large scale and interseasonal variability. For example, if you see the 2016, there's 3 major carbon waves passing from Indian Ocean and through Indo Maritime Continent to the Western Pacific. And then it's in the equatorial region. And in the 2017, you also have maybe 2 major carbon waves, and also have kind of overall slower moving interseasonal oscillation in the whole month. Okay, and then north of the equator, you'll see the equatorial waves shown by these red contours, and then we call them mixed Rossby gravity TD type disturbance. We call MT waves. There's a 4 parts of waves that originated in the Western Pacific and propagate westward. Okay, similar kind of situation. You have 2 equatorial Rossby waves. This is suppressed phase, and this is convective phase, and you have the MT waves. Okay, so I will focus on this particular 2016 because we have done a kind of detailed analysis of this particular month, and this is for the 2017. We can discuss kind of contrast. So this is the data we use. So all the data are filtered, space-time filter, following like a Wheeler and Collada's kind of approach. But I think the way we filter data following Wheeler's method, Wheeler and Hendon's paper, is it doesn't use it's kind of forward filtering, so you use for the real-time monitoring purpose. Okay, so this is why we adopt this method, because we want to also have the monitoring capability when we do this experiments. So very briefly, I'm just showing a highlight of the scale interaction in the December 2016, shown in this figure. This is the OLR anomaly in the 5 degrees south to 5 degrees north in the equatorial, between 16 east to the dayline for the December cases. And this is one of the Rossby wave, another Rossby wave north of the equator. This is, I'm sorry, the OLR is not in the, it's north of the equator, 5 to 15 north. And these are the Kevin waves, okay? And the interesting thing is you have the first Rossby wave that propagate westward, and then we reach to the Indian Ocean. This is the Rossby, the convection signal is north of the equator, but the zonal wind associated with the Rossby wave at the equator in the eastern Indian Ocean is westerly. So when it reaches to this point, it kind of interact with the Kevin wave. So the convection kind of become enhanced. And the contour here is the zonal wind in the equatorial region. Okay, so this is indicate kind of the enhanced zonal wind here is associated with the Kevin wave here. So this is the first scale interaction. Similarly, this scale interaction here is also, as you can see, this kind of wave going from MT3 waves, and this is I think this is the Kevin wave over here. So similarly, this cyclonic circulation, the zonal wind of the cyclonic circulation in the Indian Ocean over the equator interact with the Kevin wave, so that that initiate kind of make this wave more enhanced. And this Kevin wave propagate to the Western Pacific, and then if you remember, this is in the La Nina condition, so that's enhanced easterly trade wind. So when the zonal wind comes to the Western Equatorial Pacific, the two flow kind of converge. So this kind of initiate a Rossby wave and also initiate a kind of MT wave. So north of the equator, you'll see this two westward moving disturbance that is being excited here. And this Kevin wave also, I think, coincided with the onset of Australian monsoon near the middle of December during this week. So this Kevin wave and Australian monsoon onset also kind of indicating a scale interaction here. And this other, so the scale interaction 1 and scale interaction 3 are similar, as I mentioned, the Rossby wave and the Kevin wave interaction. And this is the important point of this two is you have Sumatra Islands that is very important for this interaction, making the enhanced convection over this region. And this particular, another important scale interaction is we call the Borneo vortex that form. This is in the South China Sea region. Okay, this is 5 to 15 knots. So this is kind of in the South China Sea, and this is in the South China Sea region. So this is one of the scale interaction I will focus on for the next slide. And this is the scale interaction I just mentioned that due to the Kevin wave and the Rossby wave and the MT wave kind of interaction. So this in the winter time, this South China Sea and the surrounding ocean is located in a very key location. You have a trade wind coming from the east, okay, and then the waves coming, the eastward moving waves comes to the Western Pacific warm pool region, and this is the time and the location that tend to have very enhanced wave activities. As you can see now, if you go back to this diagram north of the equator, this is 2016, this is 2017 in the winter time. As you can see, this region in the Western Pacific, you see the wave often are kind of initiated and enhanced and propagating westward because of this the seasonal cycle, and then in this particular 2 years, the La Nina condition makes a stronger trade wind. And okay, and then you have the north of from the winter monsoon, from the north-easterly monsoon coming from the north, also comes to the Philippine region over this, and then collide with the converge with the easterly wind. So these are the region, the La Nina condition makes this topography and the wave interaction even stronger. Okay, I'm sorry I didn't have this figure. This maybe I'll use this figure later to describe what I just said. So this is the simulation we did using the MPAS data. This is for the first 3.5-day simulation. We have carry out 10-day simulation. So I won't go into details. I will discuss this kind of modeling there tomorrow at the garden. Okay, so this I try to showing some maps for this scale interaction during this event. Okay, so this starts from December the 6th to about the 14th for about more than a week. So this is initiation of convection over in the early part of December, and then there's empty wave coming. And so as you show here, this is December 6th, 7th, 8th, 9th, 10th, 11th till 14th. So what I'm saying should be is shown this it can be I think easier thing in this set of figures. So this is the time you have a pronounced winter monsoon coming from the north. So you see a very strong northeasterly flow over the South China Sea. So the enhanced monsoon flow, and also you have this enhanced easterly wind. So this region you have a convergence region. So often you have a cold front, frontal zone that formed during in this area because of the encountering monsoon flow and trade wind. And then during this period, the stronger monsoon flow over the South China Sea interact with the Indo-China terrains. Okay, so you already have convection that formed in this region. This is due to the terrain monsoon interaction. Okay, and then this is what I said. This is empty waves. This is the convective part of empty wave. This is suppressed empty wave. This is labeling is done based on the space-time filtered data. It's not drawn arbitrarily. Okay, so we actually apply space-time filtered data and look at the mixed velocity gravity type disturbance. So this wave moves westward. Okay, for convective phase from this location to this location to this location. So so this monsoon flow terrain and this wave coming into, I think when the wave comes into this region, you then have a very sudden onset of we call the Borneo vortex here. That Bill Lau and C.P. Chan had analyzed such kind of phenomena in the early 70s. So the Borneo vortex in this particular case, this Borneo vortex is formed due to this very interesting scale interaction, and then that become a well-organized cyclonic circulation and move further eastward, westward. So this is the first, just using this example to show the scale interaction. Okay, so so this is the 2016, and then now you're coming back to the 2017 again. So this is the daily rainfall data in the equatorial region for the month, and this is also rainfall, but north of the equator, 5 to 15 nodes. So this, as I say, this is a broad interseasonal oscillation that propagates eastward. And then when it comes to the warm pool region and encounter the trade wind, so north of the equator, this is the time and the location you have a very active wave activities that is initiated. So this is and then this is the red contour, as I mentioned already, is the Rossby wave. And then this blue curve here indicates the MT waves. And then there's actually 3 tropical cyclones formed during this month. Okay, the first 2 actually happened when the active phase of MTO arrived to this region. So this are the track of the 3 tropical cyclones. Okay, they all form in east of Philippines, and then moving westward because of the steering flow. But during this period, actually, you have very strong cold monsoon flow coming into the South China Sea, so they actually died over this region over here. So this is the weather map of that the 3 tropical cyclones. And this is the sounding data we released and measured the wind and humidity at Dongsha Island and also Taiping Island. This is to the north, about 20-degree north in the South China Sea, and this is 10-degree north in the South China Sea, in the middle of South China Sea. So this is only I only show up to about the low part of the atmosphere up to 500 hectopascal. So the humidity is shown by the color. Okay, so the red color means it's dry, and then blue color is the green is actually drier. The blue is relatively humid than the dry. So you'll see in this region, because of the winter monsoon, it's cold. So when you have, so that the boundary layer is kind of drier relative to I'm sorry, this is the blue is the driest. The blue is the humid, more humid. So the boundary layer is humid and then dry and even drier. But during the cold surge, during the 8th, around 8th of the month, 11th, and then the later part of the month, you see the boundary layers becoming relatively more drier because it is cold air from the north. And during this part of the month, you have the tropical cyclone formed, so you'll see very strong wind and the changes. And when the cold air comes from Dongsha to Taiping, from north to south, it's getting drier. The north is dry, and then once it's to the south, it is modify the ocean, so it's getting relatively humid. So this is the sounding data. So we have. So this is a very brief introduction for the 2017 and the 2018, 16 and 17 winter interseasonal oscillation. For this past summer interseasonal variability, we carry out ongoing study. So this is the first I'm showing the interannual kind of background for the monthly mean SST from basic February, March, April, May through June. Okay, so from the SST anomaly, you're seeing kind of La Nina condition from the earlier year and gradually kind of weakening to June and July. And also you'll see this from this period, and then April, you start seeing kind of Pacific Meridional mode of the temperature anomaly, SST anomaly, forming and then persist through almost 3 months. And the La Nina, of course, is persistent and weakening. Okay, and then also you see a very interesting southward shift of the SST distribution, so making this north-south hemispheric kind of asymmetric feature getting stronger as with the seasonal march. So maybe this is part of the seasonal cycle, okay? And then this is the SST anomaly. This slightly north-south asymmetry actually is very important for the convection. So if you see the convection in the next slide, you see the convection actually north-south very strong, so north-south asymmetric. So maybe this is also related to the Atlantic SST, because if you see the warm SST, the SS distribution over the Atlantic, there's a north-south dipole kind of pattern developed from this through the years. So so this stronger Atlantic may have some influence. So when you look at outgoing long wave radiation for April, May, and June, you can see the SST is the same as the previous slide, but the convection is actually more enhanced north of the equator, but south of the equator is relatively suppressed. Okay, so this may be related to, definitely related to. So maybe you can see the next slide. So this is again the SST anomaly for the April, May, and June. And this is the near surface wind, horizontal wind, and also the OAR anomaly here. So this is something called the meridional mode. So this may be related to the wintertime North Pacific oscillation. So the atmospheric circulation drives this ocean temperature, meridional temperature distribution. And this, of course, and coupled with convection, because the near surface pressure gradient will induce across equator wind over here, and so this will produce help for the formation of convection. So the convection is formed associated with the SST anomaly. Also, you have the air interaction helping. So the convection and circulation making this system persistent through April, May, and June. Okay, so the warm anomaly and also the cold SST anomaly appear to be important for the warm anomaly SST and also suppress convection over this region over here. Okay, so this is very persistent features from I think from the months of May and June. Okay, so this is very important background for the monsoon onset, because this SST distribution and the circulation somehow make this anticyclonic circulation over the Southeast China, South China Sea, and even Eastern Indian Ocean. It may form a very extensive subtropical anticyclonic circulation, as shown in the monthly mean of May SST anomaly. This is the anomaly we mentioned. La Nina condition, and then the SST distribution, and then the enhanced convection north of the equator, and I think it's related to the SST distribution, and that helped maintain this anticyclonic circulation and the suppressed condition. So you see over the North Indian Ocean, South China Sea, and the Western Pacific are all in the warm suppressed condition. So if you look at this, so this is the monthly mean feature. If you look at the circulation, the monthly mean circulation, you'll see this broad scale anticyclonic circulation. Okay, and this anticyclonation, of course, if you look at the SST tendency for this month, it is mostly due to the surface fluxes, indicating the air interaction over a broad region over here, kind of basin scale kind of coupling is maintained, mutually maintained by the SST distribution, the cloud, and then the dynamics here. So with this background, we like to see what is intraseasonal oscillation and what contribute to the onset of the South China Sea monsoon. So this is the very simple 5-day mean velocity potential and OAR anomaly for the penta mean from April, the first penta, okay, and then through May, and then early June. Okay, so in the early April, the velocity potential show this is you have this convective phase of the overturning circulation, and this is the subsiding branch of the overturning circulation, and this associated with the convection over here. So this is the intraseasonal oscillation that formed in the early April and moving eastward, okay, and then gradually move here and then gradually dissipate. And then in the early May, in the ocean, it is a suppressed phase of intraseasonal oscillation, and this suppressed west of this suppressed phase, you have this cloud cluster form. This is kind of twin cyclone form, and then that moves eastward and then quickly develop into this kind of northward, becoming much enhanced. So this is very typical of the so-called boreal summer intraseasonal oscillation that actually propagates to this region over here. So so this convective phase of intraseasonal oscillation helps the establishment of the southwesterly monsoon over the South China Sea. So normally the South China Sea monsoon developed in mid and late May, but this year it's kind of delayed. It's late for about 1 to 2 weeks. So it didn't develop until this time. Okay, so this is because you have this suppression of the previous anticyclone that preventing the development of the monsoon over the South China Sea, and then this intraseasonal oscillation helps the establishment. But so this is the kind of another view of the intraseasonal oscillation. This is over the equator, and so the shading shows the OAR anomaly, and then the contour here is filtered MJO. So this is the one over in May, okay, and then this over equator. And north of the equator, you'll see this is the equator, the signal in the equator. But if you see the convection in this north of the equator is actually a few days lag this equatorial signal, indicating you not only have an eastward parking, you also have a northward tilt convection. That's why you have this this shift. This is the South China Sea region here. So this is the late May and early June. So you see this is through the month of May, it is all suppressed until early June is when this species of boreal summer arrived. Then you start having this convection here. Okay, but before that, not only the MGO, this Rossby wave during the later part of May, the dry phase of the Rossby arrives to the South China Sea region here. So this also suppressed the convection and delayed it until it kind of weakened, and then the MGO, the BCSO, finally takes it, make it happen here. So we are doing our field campaign during the month of May, and we are trying to decide to make intensity observations and wait until the end of May before we can actually seeing the onset of monsoon here. So this is the figure we got from Kikuchi, and showing that the intraseasonal oscillation in the month of May is indeed more closer to a boreal summer pattern than the MGO pattern. So for example, if you project this penta or anomaly over the, I think this is to the BCSO pattern, you'll see it fits the pattern much closer than the MGO pattern. So in summary, the extended weather and intraseasonal oscillation of the 2018 May season is influenced by the anomalous cooling in the central equatorial Pacific associated with the La Nina phase of the Indo-Pacific climate oscillation. The Intraseasonal oscillation emerges on western Indian Ocean in early April and propagates to western Indian Ocean and dissipates in late April. The Indian Ocean is in dry phase in early May, and the new cloud clusters develop over western Indian Ocean in mid-May and evolve into BC, so that coincide with an ER and unsettled in South China Sea monsoon in early June. Okay, and then the La Nina cooling and the intraseasonal LC interaction together sustain the anomalous anticyclone circulation and prevent the development of the southwest monsoon until early June. Okay, so this is the summary. The part that we are trying to understand is what maintains the persistent anomalous anticyclone. So this is, I think we have this speculation that the cold SST anomaly in the western North Pacific during La Nina persisting the season in spring, okay, like April, May, plays a role through an interbasin atmospheric coupling process. Okay, so this is similar to a suggested mechanism for anticyclone in summer. Okay, that was for the summer across the Indo-Pacific during the El Nino decaying season, like proposed like Bing Wang, Kosaka, and a couple of people. And also, as I mentioned, there's a kind of seasonal migration. So the ITCZ or the convection kind of move to the south. So like a Fei proposed something called the combination mode. So in this particular case, although the combination mode is just a kind of mathematical concept, the observational evidence is not very clear. But in this particular case, it appears that the La Nina and the seasonal cycle, together with the Atlantic warming, may play a role causing such kind of north-south asymmetry features. Okay, so this is the things that we are trying to work on, and that's why I invited collaborators like Meng Lu and Professor Chung-Hsiung. Professor Chung is maintaining a couple model, and Professor Meng is now a faculty in the department, so we can work together to understand this kind of interannual and intraseasonal variability in the Indian Ocean, South China Sea, Western Pacific regions. Okay, thank you.
So, any questions? It's a very complicated mechanism of selection. I think in your first slide, it shows the diurnal cycle. Doesn't there is a diurnal cycle in that area be a major rule for the intraseasonal?
Yeah, I think for the IOP of Maritime Continent project and also the ongoing Piston project, that's a very active. It's a very hot subject that the diurnal cycle in the Maritime Continent region interact with the MGO. That seems to play a very important role. So we also look into this interactions, and so the diurnal cycle in that region and also in the South China Sea region also have some common features. So in the suppressed phase of the MGO, or the intraseasonal oscillation, the length, diurnal cycle over land is much enhanced, and the ocean is kind of suppressed, especially in the South China Sea. But during the MGO or ISO convective phase, convection is more organized over the ocean diurnal cycle, and the land is kind of suppressed. So in the South China Sea region, maybe the kind of South China Sea wide land sea breeze during day and night is modulated by the MGO or the intraseasonal oscillation. So this basin-wide kind of circulation can suppress convection of the ocean or not. So that seems the case. So Professor Wei-Ting Chen in my department is working on this, and we are working together. when we look at the intraseasonal and diurnal in the Maritime Continent region, and we found that the diurnal amplitude of diurnal cycle tend to be on the leeward side of the big island instead of the windward side of the island. So that's very different from what we normally understand, at least for the smaller scale island or land terrain effect. So our investigation indicate that has something to do with the humidity distribution over the island and over the surrounding oceans, and the prevailing wind of the interseasonal oscillation that determine your advective moistening or drying. So that helps determine the amplitude of the diurnal cycle. And then in the Maritime Continent region, they call this vanguard effect. So the diurnal cycle rainfall over the island already become enhanced before the active phase of MGO. So I think, and then in the suppressed phase, it's the opposite. Yeah.
And also, I'm seeing you have profile sounding release like 3 hours.
Every two times or 4 times a day.
Each hour,
No. Each day or each 12 hours or each 6 hours. There's some IOP that we has 4 times a day.
Any cycle in the ocean and continental and very different in this part. I think if you can analyze more like a vertical sounding in a much higher frequency, it can give us a 3-dimension picture of what this means in land and ocean.
Yes, right. We have
go through this area. If you can spend a little more money to run for sounding.
We have at Dongsha we have a wind profiler, so that you have a very high resolution wind up to 15 kilometers, 10 to 15 kilometers. So the wind is pretty reliable. But for the humidity and temperature, we have a radiometer. The Central Weather Bureau maintains a radiometer, also microwave radiometer. But that instrument tends to be more difficult to maintain. You have to really take good care of it to make the data reliable. So we have seen some of the measurements. It's not very good. So yeah, so we for the thermodynamic variable, we still have to rely on maybe sounding. And we haven't done such a kind of very intensive observation yet because our budget is very limited. And also, the manpower is another problem. We realized that go to the island is very difficult because the island, for example, Taiping Island is I think operated by our Coast Guard. So they rely on the ship, the Coast Guard ship. The ship goes there like the maximum 3 ships a month. So, and their first priority is to maintain the personnel and supply, and research is secondary. So we have to negotiate with them to send our instruments and everything, helium tank, everything.
I just have one. Most people, if they look at the interaction, they look at either the wintertime, the embryo propagation, the diurnal cycle, or they look at the summertime, where the embryo, or summer intraseasonal oscillation. So, but I think your emphasis is on the transition that tend to be most typical because that is the season where there's really no dominant forcing. All the little forcings are trying to make a difference.
You mean the summer, the May?
No, in the May, April, May, and that's why it's very complicated, that situation, because it's very sensitive in the sense that one forcing which is dominant, then there's a feedback, and the system will go another way. So my question to you is that how typical? I mean, the kind of interaction you look at just one season. You look at another season, like the anti-cyclone become weaker or change sign, then your interaction will be totally different.
Yeah, for these 2 years, it happened.
Hard to do any kind of composite analysis or so that you can have some more coherent variation. That's the most difficult. This part, well, because everything is trying to have an edge, we're trying to dominate, and then you see all this multi-scale interaction going on. Once you go to the mid-summer or the mid-winter, you actually have a dominant force, intraseasonal, like the NGO becomes much stronger. And it's actually easier to look at. Your case is going to be complicated.
Yeah.
And I don't think, and you see 1 year and the next year will be completely different, even if you pick. It's very difficult to do kind of composite. But it needs to be done because sometimes you do get additional signal earlier on in terms of the onset of the
But I thought with many studies, including yours, about this summer monsoon and the summer monsoon and the intraseasonal thing in the summer monsoon. So we also did composite study, but only for the intraseasonal oscillation, not for the monsoon transition. Right. So that's why I thought maybe starting the transition, we should look into cases first. And plus, you know, with such kind of field camera, we only have 1 or 2 years data, so we have to look in anyway before we. But I thought from the case study, we can get some, I think, maybe more realistic kind of understanding about the processes, dominant processes are going on. So then we can then look at the more ontological analysis. Yeah, so yeah, we do have, at least for the intraseasonal thing, we are looking in the multi-years of data. But for this monsoon kind of study, yeah, I agree. We are looking at the transition. Okay, thank you. Yeah. So, Bill, do you want to? I can talk to him.
Sure. Yeah. He'll be here. You can take that on.